Hello everybody, and today we'll be looking at 5.2 graphs and applications of exponential functions. So in this lesson, you should be able to sketch graphs that are the form of y equals to a to the power of x and y equals to e to the power of x, and to use exponential functions as models. Okay, now, so there will be situations whereby we want to study an exponential equation. What's an exponential equation? Okay, in this case, one is y equals to a to the power of x. And what is a? A will be a number that is greater than 0. So some of the graphs that you can look at today is y equals to 2 to the power of x, y equals to e to the power of x. Okay, and then also you have y equals to maybe something smaller than 1 but still greater than 0, y equals to 0.1 to the power of x. So these exponential functions, the very first thing that you need to take note of is that a will be greater than 0. Okay, then it will be called an exponential function. The next thing, earlier I spoke about y equals to e to the power of x. What is e? Okay, so in mathematics, e is the representation of a constant. For example, one constant that you are aware of is pi. Okay, 3.1412 yada yada yada. Okay, so same thing for there's this value called e. E is also an irrational number, is 2.71828 and all. Not to worry, this exponential number e, okay, can be found inside your calculator. If you're able to, all right, now you can ask your teacher in class, try to find what is the value of e to the power of 1. You get this number 2.71828 dot 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 dot. Okay, so now, okay, today we're going to study functions. So functions describes the relationship between x and y, such that for every value of x there can only be one value of y. But the inverse is not true. So for example, one value of y, you can actually get two values of x. But most importantly, for one value of x, you can only get a corresponding value of y. Okay, now, so I introduced to you the shape of the graph, y equals to a to the power of x. So when the number a is greater than 1, examples are y equals to 2 to the power of x, y equals to 1.1x, y equals to 7 to the power of x. The graph will be of this shape over here, and notice that this graph experiences exponential growth, which means that it will always, can become, the value of y will become larger and larger as the value of x increases. Another thing to note is the vertical intercept of this graph itself. For all exponential graphs, the vertical intercept will always be x is 0, y is 1. Why is this so? Okay, because y equals to a to the power of x. When you have any value, when the x value is 0, your y value equals to 1. We have learned in elementary mathematics that a to the power of 0 is equals to 1. Hence, that's why the vertical intercept will be equals to 1. Now, similarly, when the value of a is greater than 0 but lesser than 1, what you get is exponential decay, means that the graph will be decreasing. Okay, then what also happens here is same thing, the vertical intercept of the graph is at 0, 1. Okay, one thing to note for this is as your x value approaches negative infinity, it will tend towards, but it will never touch the x-axis itself. So you notice that as you draw the graph, you sketch the graphs, there should be this gap over here. Similarly, for the exponential decay itself, it will tend towards 0, but it never touches the x-axis. So it will go on and on and on, but it will never touch. It approaches, but never touches. Okay, so now what we're going to do here is this. So I'm going to do example 7. So for example 7, if you notice the base, what is the base? Y equals to 2.5 to the power of x. 2.5 is the base itself. Since my base 2.5 is greater than 1, so in this case, for my exponential graph, it's going to look like this. Okay, and then please pay attention over here, it must not touch the x-axis. Then you can also label that this vertical intercept here is 1. And that's it for 7a. For 7b, notice that the base is 1/3, and in this case, my base is lesser than 1. So in this case, exponential decay will occur. So to draw a graph with exponential decay, we just draw this. Okay, and then we label the vertical intercept to be 1. For part C, something similar, e to the power of x. As we have learned earlier in this topic, e is 2.718, so e is actually greater than 1. So if e is greater than 1, what I'll get is a exponential graph where exponential growth occurs. So in this case, the shape of the graph will be like this. And once again, this vertical intercept will be equals to 1. That's all for example 7. Not very difficult, but you need to be able to draw these graphs or to sketch these graphs when required. Okay, now for try 7, there's 7a, 7b, and 7c. Please attempt these graphs, okay, 7a, b, and c. Pause the video, and then when you're ready, you may unpause the video, and I'll show you the answers. Okay, and I'll show you the answers in 3, 2, 1. For a, the base is 0.44 to the power of x. 0.44 is lesser than 1, hence exponential decay occurs, and the shape of the graph will look like this. I know I sound like a broken record, but it approaches but never touches the x-axis. For 7b, my base is 5.2, so since 5.2 it leads to exponential growth, so again, notice that this portion here never touches the x-axis, and the vertical intercept is once again equals to 1. Last but not least, for try 7c, 1 over e, 1 over 2.718 is lesser than 1 itself. Hence, exponential decay will occur in this graph. So the shape of the graph looks like this. Once again, ensure that it doesn't touch the x-axis, and it will intercept at the vertical intercept at y equals to 1. So that's it for try 7. I don't think it's a difficult concept. Now we move on to calculations in example 8 itself. So for example 8, this question is actually talking about the population census. So the population Y of a town X years after the beginning of 2020 is given by Y equals to 22,000 E to the power 0.15 X. So what we are looking here is X years. So for example, if you want to find out what happens in the beginning of 2021, what I'll do is from 2020 to 2021, 1 year has passed. So what I'll do is I will actually substitute into my equation 22,000 E 0.5 to the power of 1. So that will actually give me the population at the beginning of 2021. But now, for this question, what they want us to do is to find the population at the beginning of 2020. So at the beginning of 2020, what this means is that no years have passed, okay? So that means my x value should be equals to 0. We are right at the beginning. So another way to ask this question is, what was a population at the beginning? So so at the start, the x value equals to 0. So if I solve, y equals to 22,000 e 0.15 to the power of 0. Notice that e to the power of 0 is equals to 1. So the y value is simply equals to 22,000. So the population was 22,000 people. Okay, for part 2 itself, 2028. So 2028, how many years have passed? 8 years have passed. Hence, in this case, for part 2, my x value is equals to 8 because 8 years have passed. So y is equals to 22,000 e to the power of 0.15 to the power of 8 because x is substituted by the value 8. So therefore, if you use your calculator, what you will get correct to the nearest whole number is 73043. Hence, the population at the start, okay, of 2028 will be 73043. In this case, we don't round off to 3 sig fig, or we actually round off to the nearest whole number because we're talking about people. So you cannot have like point something person, you cannot have 0.2 of a person. What is 0.2 of a person? It doesn't quite exist, alright? So now, okay, please try 8, okay, and then I will give you the answers. So when you're done, okay, just pause the video first. When you're done, unpause the video. I'll carry on in 3, 2, 1. Let's go. Okay, now, so at the beginning of the experiment, beginning means that no time has or no days have passed. So my x value, the number of days, is equals to 0. So you substitute x is equals to 0 here. So what we have done here is that if we have substituted the value of x to be 0, at the beginning of the experiment, there are 50 fruit flies. After 3.5 days, I will substitute my value of x by 3.5. Hence, is 50 times 2 to the power of 3.5 equals to 566. So I round off to the nearest whole number in this case, because we're talking about number of flies. If you have issues with inputting these calculations into the your calculator, please try, okay, and sure you can get the numbers. If you can't, okay, please let your teachers know, and then we can actually run you through how to use your calculator to input like 50 times 2 to the power of 3.5. Okay, last example for this chapter, example 9. Okay, example 9 is given by this. The amount Y of a radioactive substance present after T years is given by this equation here. Okay, where A is a constant. At the beginning, there's 250 milligrams of substance. Find the value of A. So now, what I can do here is this. If I want to find the value of A, so I know that I can use this, actually, this the start of this what I call question to actually help me. So at the beginning, T is equals to 0. Okay, because beginning means no time has passed, and I know that the value of Y, the amount of substance, is 250 milligrams. So at the very start, I already have two values I can use, okay, to substitute into my equation to try to solve for the constant A. Hence, okay, I write down Y is equals to A e to the power of negative 0.2t. So my Y value is 250, A e, okay, negative 0.2t, t to the power of negative 0.2 times 0. So here will be 0. So very simply, my A value is 250. Okay, we remember from part 1, my A value is 250. So now that means that the equation is now given by Y equals to 250 e to the power of negative 0.2t. So now they tell me what is the amount present after 5 years. So after 5 years, it implies that the t value is equals to 5. Hence, to find the amount, I just write t e negative 0.2 to the power of 5. I simplify for you, you get e to the power of negative 1. If you just input that into your calculator itself, okay, what you should get is 92.0 milligram. Correct to 3SF. Okay, part 3. For part 3 itself is the amount that has decayed after 1 decade. So after 1 decade, my t value is equals to 10. So I'll write there Y is equals to 250 e to the power of negative 0.2 times 10. If you work that out, okay, your Y value in this case is 33.834 milligrams. Okay, now, question, is my final answer 33.834? No. 33.834 is the amount of the substance that is left. Okay, so this is not what we want, this amount that is left, but we want to know how much has decayed or disappeared. So in order for me to do that, I need to take my initial value of 250 milligrams minus 33.834. What I find is that 216 milligrams, okay, has decayed. So be very careful, they're not asking you for how much is left, they actually ask you for how much has disappeared or how much has decayed. So 216 milligrams has actually decayed. So now what you can do is, please try 9, pause the video, try 9, When you're ready, unpause the video and we will go through this in 3, 2, 1. Let's go. Okay, just very quickly. At the beginning, alright, I know that there was 500 milligram of the substance. So beginning means that the T value is 0 and the amount of substance is 500. I substitute that into my equation. E to the power of 0 is equals to 1. Hence, A times 1 is 500. A is 500 itself. The amount present after 2 years, what we know is that we must allow the T value to be equals to 2. I input this into my equation. What I get is, correct to 3SF is 274 milligrams. Lastly, the amount that is decayed after 4 years. So the T value is 4 years. 150.60 is the amount that is left. So this is the amount that is left, but be careful, we want to find the amount that has decayed. So this amount is still present, we want to find the amount that has in a way disappeared. We take 500 minus 150.60, okay, from here. We are left with 349, correct to 3 significant figures. So the amount that's decayed for 4 years is 349 milligrams. And that concludes 5.2. Thank you for watching.